Okay, so fantastic. Well, thank you everyone for being here. This is going to be the second of our joint TYC MMM Hub software spotlight events. And today we're very pleased to have three of the developers of the popular Onetep code, which is quite a well-used code on the tier 2 HPC resources. So Onetep is a linear scaling density functional theory code that can has a whole host of functionality, and due to its linear scaling can really scale up to very large systems, being able to treat carbon nanotube, heterogeneous catalysis, lots of large systems. And so that's made it very popular and very powerful code. So what we're hoping for today is a bit of a deep dive into the anatomy of its capabilities and of the actual calculations, maybe with a live demo as well, and to really enable new users to get onto the code in quite a simple way. And with that, we're very lucky to have some of the developers of the code. We've got Chris Skylaris, who's in Southampton, who's one of the original developers of the code, although there are other developers throughout the UK. And a few further afield, and also two members of his group that work with him closely, senior research fellow Jacek Dziedzicz and Arihant Bandari, who will do a live demo later on. So with that, I'll pass over to Chris, who's going to give a high-level overview of the Onetep code and its capabilities, and we'll probably save the questions until after he's finished. But if you have any questions, do feel free to put them in the chat. Okay, thanks. Over to you, Chris.
Okay, thank you very much, George, and thank you for the opportunity to present the code in this spotlight. I'm thanking the MMM Hub also for this opportunity. I'm going to give a brief introduction of the code as you said, and then Jacek will demonstrate a simple calculation, and then Arihant a more advanced calculation with some of the capabilities for electrolyte modeling that we have been developing recently. So this is an outline of my talk. I'm going to just very briefly talk about the theory of density functional theory and the linear scaling reformulation, and then some Onetep specific things, such as the philosophy behind the code and the things such as the basis set that we use and so on. Then I will very quickly run you through what a calculation involves, and then you will see it in practice from Jacek and Arihant. And then I will finish with a summary of the available functionality and some slides of applications. So quite a lot here, so I might skip a few things in the interest of time. So density functional theory, as you know it in the ConSum textbook form, involves solving one particle eigenvalue equations, Edgar-like equations. You get the electronic density as the sum of the square of the orbitals or bands. And it has steps such as the diagonalization or the building of the Hamiltonian matrix or the orthogonality, which are by default, by construction, steps which increase with the third power in the number of elements in these matrices, which is proportional to the number of atoms. So computationally, conventional DFT scales like this. It has this cubic scaling of the number of atoms. So it's good for some things, but if you have problems that involve complex structures, nanostructures, systems with thousands of atoms for which, for some reason, you need, for chemical accuracy, for example, or for other types of properties, you need to model the electronic interactions accurately, you cannot use conventional DFT, and linear scaling reformulation is needed. So the principles of linear scaling reformulation of DFT, the theoretical principles, were given by Walter Kohn and others. It is based on the observation that the one particle density matrix decays exponentially with the number of, with the distance of its variables. As you see here, And then linear scaling approaches, if you can express the density functional theory, the energy expression, if you can express it from molecular orbitals, if you can express it in terms of the density matrix, you can come up with linear scaling approaches by truncating the density matrix after some distance cutoff, so that the number of non-zero elements is scaling linearly with the number of atoms. So you end up with sparse matrices, sparse matrix operations, and with enough sparsity, you are linear scaling. In practice, you don't need to work directly with the density matrix. You can show it is equivalent if you work with localized orbitals or Wannier functions in other words, and you can employ you can employ methods that do not involve diagonalization and include direct energy minimization and sparse matrix algorithms. So that's all well and good, but in practice, you end up fighting with conflicting requirements. Linear scaling wants localized functions and sparse matrices. The large base set accuracy that you want to achieve with DFT needs delocalized functions and dense matrices. So the big problem in the development of linear scaling DFT methods is how to combine these two requirements. So Onetep is a product of many years of development, and we've learned from the mistakes of others through the history of these methods in the last 30 or so years. And the aim of Onetep is to have linear scaling DFT, but with the same accuracy, the same large base set accuracy as conventional cubic scaling DFT. And to do this, we use a minimal number of localized functions, localized orbitals, which we call non-orthogonal generalized Wannier functions, or NGWFs. So this is the linear scaling localization part, but then these are not fixed. They are optimized inside the calculation. They adapt to the chemical environment. So this is the high accuracy, large basis set type of approach. And also we optimize the density kernel, or the coefficients, if you like, that connect these NGWFs to build the density matrix. So essentially, it's a two-resolution approach. We have the coarse resolution of the density kernel and the fine resolution of the NGWFs that are optimized. So to optimize the NGWFs, we have a basis set, and this basis set is essentially a plane wave basis set. It's a plane wave method. So we have plane wave accuracy, but we don't use plane waves in the delocalized form. We use them in the form of highly localized periodic sinc functions that you can see here. This is how they look. And then we can impose localization of the NGWFs by using spherical localization regions and using only the basis functions, the sinc basis functions that are inside the spherical localization region. Since it is a plane wave basis set, we need to use pseudopotentials to describe the core electrons, as you do in all plane waves basis set calculations, because close to the core, the wave functions, the whole electron wave functions have sharp oscillations, and the potential, the electrostatic potential has, the nuclear potential has a singularity. These things cannot be described with a plane wave basis set. They wouldn't converge with reasonable grid spacing. So we replace these with a much smoother wave function, pseudo wave function, and a smoother potential that is produced by the pseudo potential that replaces the nucleus and the core electrons. So this is the same as in all plane wave codes, and we use pseudo potentials of the same format. Now, an example of the high accuracy that I told you about is shown here, where we have Onetep calculations with increasing radius, localization radius of NWFs, we are calculating here the interaction energy of this phenol molecule with the surrounding waters. And we can see that this converges rapidly. These are the radii we use in routine calculations every day, and converges to the value that you would get with a really, really big base set, in this case with a conventional cubic scaling Gaussian base set code. But you can do this comparison also with plane waves and other types of codes. We've made lots of comparisons like this. And it's always good to validate with the cubic scaling code just to make sure that that the cutoffs that you're using are sufficient. So let's look now at the structure of the calculation in Onetep. So we have to optimize two things. One is the NZWFs, as I said, and the other is the density kernel. And we optimize this in two nested loops. In the inner loop, we optimize the density kernel, as you can see here. And in the outer loop, we optimize with a kind of self-consistent energy minimization in each loop. We optimize the NZWFs. So for every step of this loop, of the NZWF loop, there is a completed kernel optimization. So both of these quantities are optimized simultaneously. So the end result of calculations with the code can be seen in this example. Here we have done calculations on fragments of lipid membranes, so a biomolecular system. You can see here the computational time with Onetep. This is, we start from this is the tiniest system, I think, here. And we go in this example up to 50,000 atoms, and you can see the linear scaling behavior. While this is a conventional cubic scaling DFT code that, as you can see, runs out of steam very early. Before probably you reach 1,000 atoms, it becomes unfeasible. So, so we can see how we can run big calculations, and this happens, you know, in all materials. You can use it also on solids, on crystalline solids, on you know, any kind of material that you can do conventional DFT. You can also do linear scaling DFT with Onetep. It just happened that in this example, I'm showing biomolecular systems. So in order to run Onetep, I'm just showing you here the kinds of things that you need to consider. The requirements are pretty typical for cluster, you know, like a multi-core cluster. We have a flexible input format. You can find documentation on our website. You need to supply pseudopotentials. And also we have a tool, which we call it the Onetep launcher, which helps set up the environment and run the calculations correctly and avoid perhaps some mistakes you would do it if you run Onetep directly. So we recommend using the Onetep launcher. So this is the input file. It has keywords of different types, you know, integer, Boolean, string, real, physical, that come with units, although they have default units, which are atomic units, but you can also put other units. And we have also data in blocks. And this is an example of how a very simple input file looks. This is the formaldehyde molecule. So this is the zinc kinetic energy cutoff. This is the base set, basically. These are the lattice vectors, the coordinates of the atoms. These are the NZWF radii here, and these are the pseudopotentials. And then when you run this, you see at the beginning a banner with some information with the code, developers, contributors, and the version number. Then you see some other information as the code starts the calculation, and here is some information about the parallelization. It has hybrid parallelism, MPI and OpenMP. Some information about the grids that the code will use, and also the kinetic energy cutoff that is selected in practice. And then some information about the initialization of NZWFs. They are initialized to atomic orbitals. And then follows the main part of the calculation, where you can see these two nested loop structure. This is the inner loop, where the density kernel is optimized. You can see it here. And then this one here, this is one iteration of the outer loop where the NZWFs are optimized. And this continues. It's a conjugate gradients minimization in each loop, conjugate gradients minimization of the interacting energy. And in the end, it converges. It should converge in about 10, 20 NZWF iterations. As you can see here, you get the energy and also and all sorts of other information, such as energy components and so on. So you will see more examples in what will follow from Jacek and Arihant. I just wanted to just kind of give you a first idea of how the code looks when it's running. Now I'm going to summarize the functionality of the code. So we have all sorts of exchange correlation functionals, as you can see here. We have LDA, GGA, non-local functionals, meta-GGAs, and also Hartree-Fock calculations and hybrid functionals. And this is a feature which we have recently speeded up by a lot, so we can run calculations with several thousand atoms there. We have a paper in preparation on this. We can do spin polarization, DFT plus D with empirical various flavors of empirical dispersion, DFT plus U, charge constrained DFT, finite temperature DFT for metallic systems, and also embedding. We have embedding mean field theory, so embedding one level of theory inside another. We can do excited states with various flavors of time-dependent DFT. We have all sorts of boundary conditions, periodic boundary conditions, open boundary conditions, electrostatic embedding. So all of these things have been developed over the years. Core electrons, so we either use non-conserving pseudopotentials, as I showed earlier, but we also have projector augmented waves. And we have a variety of simulation environments. So we can do the conventional type of calculation in vacuum, but we also have a highly developed implicit solvent model, and more recent developments are implicit solvent and electrolyte, and also electrolyte and applied voltage. So you don't work in a constant number of electrons, but in a constant voltage, and the electrons can change as it happens in electrochemistry applications. We have atomic forces, so we can do geometry relaxation, transition state search, ab initio molecular dynamics. We can visualize various quantities such as the orbitals and the NZWFs. We can even do atomic orbital calculations by keeping the NZWFs fixed and initializing them to various levels of atomic orbital base set, from single zeta to double zeta plus polarization and so on. And we have a variety of electronic properties. I'm showing here some of them, all sorts of densities of states, atomic charges, multipoles, and so on and so on, energy decomposition analysis, electron transport, and so on. So this is a very quick tour of the types of things that the code can do. I have 2 or 3 slides here just showing some pictures from applications with the code. So this is a theme we have in biomolecular simulations in drug design applications. So trying in challenging cases where force fields have difficulty representing the interactions, we want to use DFT to capture the interactions between potential drug, a ligand, and the protein. And we don't just calculate energies. We calculate free energies of binding in solvent in order to capture this free energies of binding, which is the critical quantity in computational drug design. So we have some encouraging results there with the simulation we described in these 2 papers, and there is more ongoing work on bigger proteins, on more complicated proteins than this one. Another area is catalysis. So these are calculations on in collaboration with Johnson Matthey and the Peter Nellis group in Oxford, who do electron microscopy. So these are calculations on on platinum nanoparticles for catalytic applications. And what we found in this work is that ideal shapes of nanoparticles have quite different properties than the real shapes that you have in experiment. These two are structures that have been obtained from electron microscopy, from techniques that our colleagues in Oxford developed to give us the coordinates. And we found that in terms of the catalytic activity that can be measured by descriptors such as absorption energy of molecules, the structure of the particle is very important. And we did this with calculations with Onetep. And these are electronic descriptors that we developed to describe the size of the nanoparticles, so the colors of the sites, as you can see in the pictures. And another application here is in organic photovoltaics. So these are time-dependent Edft calculations where we are able to use Onetep to increase the complexity growth from simple models to much more realistic models and understand here excitation and charge transfer effects that happen in organic photovoltaics. So this is the active material is called bulk heterojunction. There is a polymer which absorbs the photon, and then the exciton is split and the electron jumps into this fullerene material phase. So we are able to model these using large-scale calculations with Onetep. So you can find more information on the Onetep website, including manuals, keywords, tutorials, and so on, and also how to obtain a license for the code. UK academic licenses are free. Non-UK have a very small fee. And also you can ask, and there's also a mailing list, you can join there. And you can ask myself and Jacek and Arihant, but also the rest of the Onetep core developers. This is the Onetep developer group that you can see here. You are welcome to contact us if you would like to start with the code, or if you have any questions about the code. And obviously, you can. It's also good to write to the mailing list, but because there's quite a few developers in the UK and abroad and users that would be beneficial if you can communicate with them also through the mailing list. So that was my introduction for Onetep. So that's the end of my talk. We can have questions if there are any, or we can move to Jacek and Arihant's parts of the spotlight. Thank you very much.
Thank you very much, Chris. If there are any burning questions now, then certainly now is a good time to ask about kind of overall functionality. Mm-hmm. But if not, I'd be also keen to move on and really see the anatomy of a real calculation, which I think might be quite useful for people. So are there any questions now? Yes, Tamas.
Hi, thank you very much for the talk. I was wondering if stress calculations and variable cell molecular dynamics is implemented in the code.
The answer is simply no. If you wanted to optimize the lattice vectors of a crystalline material, I can tell you how to do it manually, and I can point you to a couple of papers we have with examples, but we haven't implemented stresses yet.
Okay, thank you.
Excellent. That was nice and quick. Are there any other questions? Okay. If not, there will be chances to have a more extended discussion at the end of the talks. But I think it would be good now to move on to
George.
Hello.
We can't hear you.
Yeah.
Chris, do you want to unshare your screen? I think. Thanks.
Okay. I think I've stopped sharing.
Yeah, perfect.
So is Jacek now?
George, I think we've lost you.
Yeah, no, I'm here. I'm here.
Okay. So
yeah, sorry.
shall I
Are
start,
you
or?
able to share? Yeah, I'm just hoping you were able to share your screen.
Yeah, I'll start with that in a moment. Okay. Let me see. I hope it works now. So
Perfect, yeah.
I'm Jacek Dziedzic. I'm one of the Onetep developers, and today I'll try to show you how to run a basic Onetep calculation and maybe look at the results. As a test system, I will be using a so-called tennis ball dimer, which is a simple model of a protein ligand binding site. And this has come from our early paper where we talked about combining Onetep with force field MD simulations and sampling structures generated from a force field. So the thing you see at the top here is this so-called tennis ball dimer. With a little bit of imagination, you can see where the name came from. It looks like a sliced tennis ball. And this is a good model of a binding site. And here actually on the right, you can see inside this binding packet of this tennis ball dimer, there is a small molecule, which is methane. So I'll be using this as our test case. This is a system that is slightly less than 200 atoms. So I'll be running this on Yang. I prepared my directory with a calculation. You can see several files here. The .dat file is the Onetep input file. I'll go through this in a moment. The XYZ file is simply our structure of this tennis ball dimer, so just the coordinates of this thingy in angstroms. The regpot files are the files with the pseudopotentials that Chris mentioned. So this is some additional data about the pseudopotentials that you should not worry about because it comes prepackaged with Onetep, or else you can always find this for free on the web. I'll maybe start with the submission script because once we deal with it, I can start the job and then I can talk while it is running, hopefully. So this is my submission script. We also give this with Onetep, so you don't have to worry about creating your own. And actually, there is just a little bit that you need to adjust. Everything that is between this line and this line, you should probably adjust to your system. Here is the name of the job. So I put in demo job. This is the maximum runtime, which I set to 1 hour. And then I need to specify how many CPU cores I want for this job. We were allocated 4 nodes on Yang. A node is 40 CPU cores. So this is why I'm saying I want to run this on 160 cores. That's quite a lot for a small system like that, but we want to finish this quickly. We want this to run quickly. Now, Onetep employs hybrid parallelism. That means that it uses both MPI processes and threads. So each MPI process spawns threads, and this is what we'll be using here. I'm telling it to spawn 4 threads from every process. So 160 divided by 4 gives me 40. So I will have 40 MPI processes. Each will spawn 4 threads, and that's how we are going to saturate 160 CPU cores. The last thing to edit would be to set the path to the Onetep launcher. So this is the bash script that Chris mentioned that is a part of my Onetep installation. It's in the utils directory, and I just have to say where it is. This launcher takes care of everything, things like environmental details, like stack sizes, OpenMP, number of threads, and things like that. So now that I have this edited, I can just submit it to the bash, sorry, to the queuing system, to the batch system. So I just queue sub this, and my demo job has been submitted. It takes 2 minutes to start, I think, on Yang, and 7 minutes to run. So in the meantime, we can take a look at what we have here in this input file. So this is my input file. It's not very long because these are just some basic keywords. I start by saying what the charge of my system is. It's a charge neutral system, so I'm saying charge 0. Actually, this is by default, so I don't really have to say this if it's a charge neutral system, but I just wanted to show it to you. Then I'm specifying the cutoff energy, which is a little bit like the resolution or something that is related to the quality of our calculation. The higher the cutoff energy, the finer the grids are on which we operate. 800 EV is a very reasonable default for a standard calculation. Then I'm selecting the exchange correlation functional to a well-known PBE functional. So this is a typical functional favored, let's say, by physicists. I am turning on this empirical dispersion correction that Chris briefly mentioned when talking about the capabilities. So it's a correction for a deficiency in density functional theory, which makes biochemical systems behave better or to give more accurate results. And then Chris mentioned the inner loop and the outer loop. So in the inner loop, Onetep optimizes the density kernel, and in the outer loop, it optimizes the localized orbitals, these so-called NGWFs. It has some good logic for determining how many inner loop iterations it should do, but you can override it. And here I'm just asking specifically for 5. I'm saying the minimal number of iterations is 5 and the maximum number of iterations is 5. So I'm always going to get 5. I'm setting the output detail to normal so that I don't overflow you with too much information. We typically like to run in verbose mode, which prints out a lot of stuff, but that will probably be too much for today. I am asking it to do properties. So at the very end, it will calculate things like Malikan charges or electrostatic potentials or electronic density, and it will print them out or write them to a file. And these are normally written to cube files. So it's a file format for exporting scalar data. I don't really like cube files. I prefer DX files. So I'm turning off the cube files. I'm saying cube format false, and I'm turning on this DX file format, and I'm asking it to calculate forces too. And then we're almost done. I am defining my simulation cell. So I'm saying this is my simulation cell, which is 67 Bohr. Well, the edge is a 67 Bohr, and it's a cube. So in all 3 Cartesian directions, I'm having 67 Bohr. Then I'm defining the species that I have in my system. So as you can see, I have oxygen, carbon, nitrogen, and hydrogen. Oxygen has an atomic number of 8, carbon is 6, nitrogen is 7, hydrogen is obviously 1. And then I'm saying how many localized orbitals I want on each of these species. So for a minimal basis on hydrogen, I only have a 1s2 orbital, so it will be enough to have just one NGWF in a minimal basis. Nitrogen, carbon, and oxygen are p group elements, so I want to span s and p. So that's why I have 4 NGWFs, 1 for the s orbital and 3 for px, py, and pz. Actually, Onetep has a good logic for determining this automatically. So if you don't want to be bothered, you can just put -1 here, and -1 means determine this for me automatically. And the last parameter here is the radius, the localization radius for these localized orbitals. 8 Bohr is a decent value for a start. You might want maybe to use 9 or 10 for more accuracy, or 7 for more speed, but for today, I think 8 is quite fine. Then I match each of these species with a pseudo-potential file. So these are the files that I showed you here. Oh, it's running already. So these are the 4 pseudo-potential files, 1 for each species. So I am matching my species with these files. And as a last keyword, I'm saying where my structure is. So I'm saying positions XYZ file, and I'm giving the file name of this structure, this XYZ file. So maybe while it's running, I can show you what the XYZ file looks like. So this is my structure. Maybe I'll just switch a few things around so that it looks more reasonable. Okay, so this is my tennis ball dimer. And if you look closely, you can see the methane molecule here. Inside this binding packet is hidden the methane molecule. So this is my input, 181 atoms. Okay, I believe the calculation is running already because I can see some output files. It hasn't completed yet. I can see my output file growing. So while it's running, I can maybe show you what you can see in the output. First, you get a few messages from this Onetep launcher. So it tells you where it is running, what the process IDs are, what is the name of my input file, in which directory I am. This is useful if you want to come back to this output file in a year or 2, so you know where this was running, which machine this was, and so on. This launcher then tries to determine what the executable is. So it figured out that it should run this Onetep executable from some logic, and then it sets up the environment. So all the things that you don't want to know about stack sizes, number of threads, process stack sizes, and so on. So all the boring details it just sets for you, and then it runs Onetep, and whatever you see later on comes directly from the Onetep calculation. So starting from here, you get the output of your Onetep calculation. You get a banner at the very beginning that tells you which papers to cite. Then it tells you on how many processes it's running. So like I promised, you have 40 MPI processes. Each of them spawns 4 threads. So you are saturating 160 CPUs. Then you get an echo of your input file. So just for reference, you can see what parameters you set up. And then you get some information on your system. So it tells you the details of your pseudo-potentials. This is a very important part. It tells you how many atoms you have. So this is the size of the molecule, 181 atoms. You have this many NGWF, so these localized orbitals. Projectors I won't go into now. This is the size of your grid. So my simulation cell is 132 grid points by 132 by 132. This is the grid spacing. So this tells you how fine your grid is. It's about half a Bohr between grid points, and that corresponds more or less to the kinetic energy cutoff I asked for. I asked for 800 eV. It got rounded to, for convenience, to 802 and a little bit more. These are some details about how the system is distributed across MPI ranks. These are some boring details. And then we actually start running. So these 5 iterations that you see here are the inner loop that Chris talked about. You can see the energy after each iteration. You can see it is going down monotonically, just like you would expect. You are optimizing it. After all, you can see the delta energy. So the change in energy in the last column, it's negative. So that's what you would expect. You want to go down in energy. And the RMS gradient and the commutator are some internal parameters that let you assess if everything is going fine. They should be going down as well, and they should be reasonably small. And after these 5 inner loop iterations, you take one step in the optimization of the NGWFs. So your orbitals are now optimized, and they are improved using a line search. We predict what the total energy is going to be after this line search. Once they are slightly modified, we write them out to a file, because you might want to use this in a future calculation. And then we go back to this inner loop. So we do, again, 5 iterations of this kernel optimization, and we keep repeating this. So we are doing NGWF iteration 2, 3, 4, and so on. I can see how far we are now. Oh, it's actually practically complete. So I can show you what the output looks like. So after iteration 11, it deemed the self-consistency process to be finished. This gradient, so essentially the change in the NGWFs was lower than a set threshold, so they were practically not being modified anymore. We've reached convergence. In the end, you get a breakdown of the components in the energy. So all the DFT energies, all the components of the energy in DFT are printed out here. You see a short summary of the calculation, so how the total energy changed in these outer loop iterations now, without going into the details of the inner loop iteration. And now it is still writing out the files, so I cannot show you what comes out later. You can see it is now outputting the DX files, but well, I can show you this because I had it pre-calculated before, so I can show you what goes on later on. So after these files are written out, so this stage here, you get some simple details of your system. So for instance, here by default, you see the Mulliken atomic population. So it tells you it's like a breakdown or a way to ascribe charges to individual atoms. It's not a perfect way of doing that, but it's a very simple scheme. So you can see, for example, that you have XS electrons over a half of an electron of an XS on oxygen, and you have, let's say, a loss of electrons from the hydrogens in this system. Okay, so this tells you the Mulliken populations of every atom in your system. Then it tells you a little bit about the bonds in your system. So it starts from the shortest bonds, and you can see, let's say, between nitrogen atom 3 and hydrogen atom 4, there is a bond of this length, and you get this many electrons contributing to this bond. I'll scroll quickly through this because it's a long thing. And then at the end, you also see a breakdown of the occupancies. So you can see what the energy levels are and where the electrons go. So this goes from the bottom, from the lowest lying energy levels. You can see they are fully occupied by electrons. Then you have a band gap, not a big one, but you can see 0.117 Hartree of a band gap or a HOMO-LUMO gap. And then there are unoccupied orbitals here, so they have 0 electrons on them. So this is a 0 Kelvin calculation. So you have either 0 or 1 occupancies. There are no fractions of an electron. Later on, it just tells you that it is writing out all those interesting orbitals. So the highest occupied molecular orbital and the lowest unoccupied molecular orbital, so the frontier orbitals, you get them written out to files. You get the density of states calculation. You get a breakdown of the forces on each atom. So I asked it to calculate forces, and it tells me what the forces are on every atom. And at the very end, you get information about timing. So this took 480 seconds, and you can see where it spent most of the time. If you are a developer, you might want to look at this table. So it wrote out this DX file, so maybe I can show you what it looks like. So for instance, I can show you the frontier orbitals. So I'm loading up my molecule into VMD. I'll just try to fine tune it a little bit. So this is just the molecule. I'll turn off the perspective so it will be slightly easier to see. And I'll work a little bit on this frontier orbital. So let's say I want to see the highest occupied molecular orbital. I will color it, let's say yellow. And you should see it here, right? So this is my highest highest occupied molecular orbital. It's like an isosurface of this thing. And I'll show you the lowest unoccupied molecular orbital just for comparison, just to see what it looks like. Let's say I'll make it red, maybe. And there you see, this is the LUMO. So you can easily plot this frontier orbitals, and if you are a chemist, you can infer some information from what they look like. You can also plot potentials and densities, and you can actually even plot the density and color it using the electrostatic potential. This is slightly more involved, so I just prepared this for you in advance. You can get a picture like that, which is my tennis ball dimer. The blue thing is the electronic density, one isosurface of the electronic density, and it is colored in red depending on what the electrostatic potential is. So you can see that interesting things actually do happen around this binding pocket here. Okay, so these were just the basics, how you can run a short calculation. Let me just verify that it actually did complete on Young. It looks like it did. Yes, it finished correctly within 460 seconds. So not bad for something that was almost 200 atoms. I think I'll stop here, and Arihant will be able to tell you more about more fancy features of Onetep.
Fantastic. Thank you very much, Jacek. It was very clear. I think, are there any quick questions for Jacek before we move on? If not, let's move on to Arihant. Thank you, Jacek.
Thanks.
Yeah. Hello, everyone.
Do you want to share your screen, Arihant?
Yeah. So I hope you can see my screen.
Looks perfect to me. Thanks.
Yeah, so I will be showing a calculation on a graphene sheet with an adsorbed sodium ion on top of it. So it's a periodic system, which is periodic in the AB plane, and there's a large vacuum in the C direction. So first we will do a calculation in a vacuum environment, followed by the solvent and electrolyte environment. So I will go to the job directory, and I have these files, which Jacek also showed you earlier, the input file, the structural XYZ file, the pseudopotential.export file, and a job submission script. The job submission script is same as that shown by Jacek. We are doing calculations on 160 cores, and we have 4 open MP processes. So there are 40 MPI across 4 open MP, giving a total of 160 cores. And I will submit this script first and then start talking about the details of the calculation so that it runs in the background. And now we will move on to the job submission input file. So this is an input file for the calculation of a periodic graphene sheet with adsorbed sodium ion in electrolyte solution. So the first block is the species. We have a sodium ion atom and with 4 NGWFs, and they are specified with 7 Bohr radii. And we have carbon atoms again with 4 NGWFs and 7 Bohr radii. We give the pseudo potential information here, the name of the pseudo potential files, followed by a block of lattice vectors in Cartesian coordinates. So I will show you this file. So this is just an orthorhombic cell with 17 angstroms in XY and 31 in the Z direction, which is the longest one. The position is read from the sodium graphene.xyz file. It contains all the coordinates of the 112 carbon atoms and 1 sodium ion. And then the charge on the system is 1 for the sodium plus ion, and we are doing it in periodic boundary conditions. So we use a multi-grid solver to solve the electrostatic potential, and which uses periodic conditions. The ionic interactions are again periodic, so it's the pseudo potential. And also smeared ions we use for the calculation of the electrostatic potential. We use smeared ions instead of the point charges. And the van der Waals forces are and energy is also calculated with the periodic boundary condition. Now we turn on the solvent environment. It says implicit solvent true. So it specifies whether to do the calculation in this implicit solvent or not. If it is false, it will be in vacuum. We say include apolar terms. So apolar terms are the cavitation, dispersion, and repulsion terms. These are interactions with the solvent. So we make this true. And also we use smeared ions because this is required for a calculation in solvent. And auto solvation true does a calculation in vacuum before starting the solvent calculation. So we will do first calculation in vacuum, followed by calculation in solvent. Now we can specify the parameters of our solvent. So we are doing a calculation in aqueous water medium. So water has a permittivity of 78.54. You can use any other solvent such as ethylene carbonate, which is used as a solvent in lithium-ion batteries, and it has a permittivity of 90.7. Then we have the dielectric permittivity function, and we specify it to keep it fixed. We can also use a self-consistent cavity, which changes during the course of calculation, which is more accurate but takes more time. So we'll use a fixed cavity here. And there are some model parameters which specify the shape of the solvent cavity, such as solvent beta and density threshold. These can again be adjusted and played with to give a more reasonable solvent cavity. And then for the calculation of cavitation, dispersion, and repulsion terms, these are taken to be proportional to the solvent's surface tension. For water, this is around 0.07415 newtons per meter. For any other solvent, for example, ethylene carbonate, it is 0.0506. So these data can be found from the literature regarding the choice of your environment, and you can run a calculation in any solvent environment as you like. So the apolar scaling factor tells the constant factor by which the cavitation, dispersion, and repulsion energy is scaled by as proportional to the solvent surface tension. Now next we will go to the electrolyte. So we are using a Poisson-Boltzmann electrolyte, and we use a full Poisson-Boltzmann equation. At the temperature is 300 Kelvin, and we include the device screening. Now we specify the electrolyte concentrations. We have electrolyte with positive charges of 1 and negative charge of -1. So it's like KCl or LiPF6, and the concentration is 0.5 molar for both of them. So the KCl will dissociate into 0.5 molar K plus and 0.5 molar Cl minus. But these are point ions like Poisson-Boltzmann description. Then we specify a neutralization scheme. So our charged electrode is neutralized by this counter ions. So we will see that there will be more negative electrolyte surrounding the positive charge, and it will be done automatically by the solver. Next, we describe the accessibility radius. So how close the electrolyte can come to our quantum system. So this has several parameters. So first, the type of the accessibility function we want to use, the steric potential or the accessibility function. So the steric potential type is M is a smooth hard sphere potential. So we have error functions around the atoms, and these are smooth. So there is a not an abrupt transition, but a smooth transition for how much the electrolyte can access the quantum region. So the accessibility is 0 close to the quantum region and 1 in the bulk electrolyte. So later on, I will show you the electrolyte concentration, so it will become more clear to you. Then we set the approach distance based on 2 parameters. One is the density isovalue, which controls the size of the, you can say, the atoms, the quantum atoms. So for example, a density of 0.002 will set the size for how close electrolyte can come close to the sodium ion. And then we have on top of it a solvent radius, which is 3 Bohrs. So on top of that thing, we have a 3 Bohrs extra region to accommodate for the solvent atoms. So we have the electrolyte, which is away from the solute by a solute shell, which is determined by the density of 0.002, plus a solvation shell, which has a radius of 3 Bohrs. So this gives a total radial cutoff of around 5.3 Bohrs around the sodium atoms and 6.3 around the carbon atoms. So you can see the electrolyte can come more closer to the sodium as compared to the carbon. And now we have specified, so these all were the keywords for the electrolyte. Now there are some normal keywords that go into the calculation. So unlike Jacek, who showed you an LNV calculation, we are doing a Edft calculation, which allows fractional occupancies and is more suitable for systems with which have very less band gap and which are actually metallic. So we specified to use the Edft by specifying it as true. The maximum number of iterations that we want to do in the inner loop of Edft, it's 10. And the smearing width is 298.15 Kelvin, same as room temperature. We can do it at higher temperature as well. The spin is 0 and spin fix is set to 1. So we are doing a spin polarized system here. And for the first iteration, it keeps the spin as fixed and then it relaxes the spin. And there are some normal keywords. We are using a cutoff of 500 EV. So this is a bit low, but you can choose a higher, but it takes more time. For demonstration purposes, I chose 500 EV. And then there is a Ngw threshold cutoff. So this specifies the convergence criteria on the outer loop. Whenever the gradient, the Ngw gradient is less than 1 e minus 5, the calculation will stop. And there is a convergence criteria on the electronic total energy, which is set to 1 e minus 4 electron volts here. And then for linear scaling computational cost, we can specify a kernel cutoff. So it will make all the elements of the density matrix, which are beyond 30 Bohrs, to be 0. You can increase this to, let's say, 1000 Bohrs if you don't want any elements to be 0 and want fully accurate calculations, but those would be cubic scaling. To get the linear scaling behavior, we need to truncate the density kernel elements. And then we specify the exchange correlation functional, which is PBE, and the dispersion. So we are including D2 van der Waals dispersion correction here, which is necessary in graphene. And then we specify the maximum number of NGWF outer loop iterations as 20. So I'm giving you more detail here, but this might not be required, and you may specify very less keywords, and it will take the rest of them as default values. So there are some keywords regarding the output. We want to keep the detail as normal, and we want to write the density kernel, the Hamiltonian and the NGWS do properties true, and solvation properties also true. And for producing the output format, we are using DX. And there are some parameters related to the DLMG. DLMG is the solver for the electrostatic potential that we use along with Onetep. So now let's see the calculation. So it has started, and there are already some files which have been produced in vacuum already. So let's look at the output now. So this is the first few lines are from the Onetep launcher script, and then it's the Onetep banner as showed by Jacek. Now the parallel information, we are using 40 MPI processes, 10 MPI on the same on 4 nodes, so 40 MPI, and each MPI running 4 OpenMP threads. And then it reiterates the input file. And then it produces the information about number of atoms, the NGWs, and the projectors, the piecing data, which it depends on. So we choose a 500 EV cutoff, and it so you can see that the cutoff along the different direction is different. So basically it calculates the number of grid sizes according to each direction. So, and then this information, which I will not go too much into detail. We will like to go. So here you can see that the D2 correction has been included. It includes a constant energy of minus 0.234 from the D2. And it starts the calculation in vacuum. So this is the EDFT inner loop. It converges after 9 iterations and writes the density kernel and Hamiltonian to these files and calculates the commutator. And now we advance, we go to the next NGWF iteration. It's not converged. The gradient is more than the tolerance. And we do a line search and update the NGWFs and go to the next inner loop. Here you can see the EDFT is converged in 8 iterations. And so on and so forth. So this continues again and again. And the vacuum calculation has converged here So in 9 iterations with this total energy, and it has started writing these output files. And this is the Mulliken population analysis in vacuum. And also the bonds. And also the occupancies and their energy levels. So you can see that the HOMO-LUMO gap is quite low. So it is advisable to use EDFT in these systems with very low band gap. And you can see that the occupancies are also fractional. And for a different system, you can also see within a lot of variations such as 0.5 occupancies, 0.6, 0.7, etc. And it is writing the orbitals. And now it has started the calculation in solvent. So we are using an electrolyte, which is 0.5 molar and which has charges +1 and -1. This is the cutoff we specified for the electrolyte accessibility region. And it has started the calculation. So within each calculation, the DLMG solver calculates electrostatic potential and we neutralize it with the electrolyte. So the calculation updates the concentrations of the electrolyte. You can see the potassium has 0.4 molar concentration and chlorine has 0.6. So the potassium ion concentration has decreased. The chlorine ion concentration has increased because the system is positively charged, so the more negative electrolyte comes near it. And so on, the calculation proceeds. We'll see current status. So it has been completed now. So it took around 671 seconds for 113 atoms, which involved 2 calculations in vacuum and solvent. And at the end, it prints all the necessary information for the calculation in solvent, including a breakup of all the energy components. The calculation of the solvation energy is also printed here. So the solvation energy is the energy in solvent minus the energy in vacuum minus the energy of the pure electrolyte. So it is 2.8. Positive solvation energy, which requires that means that the system is less stable in solvent as compared to vacuum. And here also in solution, it produces all the data for the occupancies, Mulliken population analysis, and it prints the summary of the calculation. So here the calculation completes in around 12 NGWF iterations. So now we can also visualize these files. So it prints a lot of files. The output.dx contains the output electrostatic potential and out BIN concentration is printed in these files. Also, you can visualize the electronic density and a lot of other information. So I will show you the electrolyte concentration. So here you can see that the positive electrolyte depletes. It is positively charged. The sodium is positively charged, and the negative electrolyte increases. The negative electrolyte concentration goes up to 4.67, whereas the positive electrolyte goes up to 0.47. And here I have plotted the electrostatic potential in the system, and you can see the polarization created by the presence of this positively charged sodium. And so this is a brief demo, and we will be happy to take any questions if you have.
Fantastic. Thank you very much, Arahant. I'm aware we're slightly over time for the hour, but are there any questions, Arahant, or indeed any of the speakers on what they showed?
Hi, could I ask some question? I think it's very impressive, the capability of the simulation in such short time. I have a, so for the sodium and graphene system, you used implicit solvent. I guess it's possible to use also explicit solvent. Is that
Yeah,
right?
so we can use explicit solvent atoms around the graphene sheet.
Yeah.
And because we are using a linear scaling DFT, it should compete reasonably fast. So what is important is you need to do a lot of different configurations of the solvent, because the solvent atoms in explicit solvation can be oriented differently, and taking an ensemble average over all of them, you can get properties. But it is
So
more computationally involved. Yeah.
yeah. So we've done similar simulations, but using VASP, and which is quite slow. And we've also done ab initio MD simulations to look at the interaction between the graphene sheet and the explicit solvent. Is the one type package also able to do similar simulation?
Yeah. We have a better electrolyte model than VASP because we include a full Poisson-Boltzmann equation, whereas VASP only includes the linear version of it. So you get much accurate, and we have a lot of additional energy terms. And also you can apply voltage to these graphene sheets.
Yeah.
So,
so if say we have researchers who would like to pick up this amazing package to use this, is there any like training opportunities?
Yeah, I think you should contact Chris. You can contact him via email, and and any future training opportunities or collaboration opportunities he would like, he will inform you.
Okay. Oh, one more question. Sorry. Is this package able to do notched band gap?
Yeah, notched elastic band NEB calculations can also be done, and this will give you the energy barrier for lithium ion migration or diffusion on the graphene, and you can calculate activation energy barriers and things like that. Yeah, you can do it.
Okay. Yeah, that's great. Brilliant.
Thank you very much. Okay, I think I'll draw things to a close here, but this will be recorded, or has been recorded, and will be hosted on the TYC and the MMM Hub web pages for people to watch at their own leisure. So I'll just thank again the speakers, Chris, Jacek, and Arahant, for a very clear introduction to the Onetep program. So thank you very much.